So the goal of this video is to be able to describe energy and the types of energy that we can have, describe energy transfer between types of systems and surroundings. And we're going to see that there's an important distinction as we think of energy transfer between a system and surroundings, and what kind of system that is going to help us understand that. In addition to that, we also want to be able to look at state functions and non-state functions and how that relates to this idea of energy transfer. Now, before we can actually just talk about these bigger ideas, which is what we want to be able to attain by the end of this video, is that we want to make sure we have some nomenclature down. So thermodynamics is a study of heat or energy transfer. And a lot of times we're thinking of that energy transfer between a system and surroundings. Now, underneath that umbrella, we have the ability to describe physical thermodynamics, which is looking at the relationship between energy transferring or unchanged matter. So what that means, there's no reaction occurring when we're looking at physical thermodynamics. So that would be an example where maybe I got a coffee mug. Into that coffee mug, I'm going to add some hot water. And as I add that hot water, we don't have a reaction occurring, but we're going to see that we're going to have energy transferred to the mug from the water, and that's going to make the mug feel warm. But again, we did not change the fact that we had a mug or that we had water here. There's no reaction occurring. Now, when we think about thermochemistry, this is looking at energy given off or absorbed by reaction. So now we have a reaction occurring, and we're thinking about the process where we're going to have some relationship between potential kinetic energy. Some of the bigger ideas we'll see is this idea of entropy and enthalpy. And because we're looking at a reaction, we're looking at a change. And that change could correspond to a change in enthalpy, H, a change in entropy, S, maybe a change in kinetic energy, or a change in potential energy. So now in order for us to be able to understand those, we also want to make sure we have the ability to distinguish by what we mean by kinetic energy or potential energy, specifically when we're looking at the idea of thermochemistry and reactions. So let's go ahead and define those things. When we're looking at systems and surroundings and energy change, we want to make sure we understand what we define by energy. So energy is the potential or the actual working of a force that causes change. So we either have stored energy that we could possibly cause change, or we have movement energy that is causing change. And we broadly break that out into kinetic energy, which is movement energy. And a lot of times in chemistry, we like to think about molecular kinetic energy. So that would be where I have maybe a container. Inside of that container, I got a bunch of molecules, and those molecules are moving around. So those molecules have, or atoms, or whatever we want to think about, have some amount of energy as they're moving around, the kinetic energy. We also have stored energy, so it's available to make some change occur. And when we talk about potential energy, when we're talking about chemistry, a lot of times we think about bonds that are going to break or bonds that are going to form, right? And that is what a chemical reaction is. We're breaking bonds and we're making bonds. And so when we're talking about a change in potential energy, that's a change in bond strengths that are occurring. We're either making weaker bonds or making stronger bonds. Now, as we have these changes occur, we want to talk about how do we define where that potential energy goes to or comes from, or where that kinetic energy goes to or comes from. So in order for us to do that, we're going to define what we call a system and the surroundings. Very broadly, we define the system as being what we're studying as undergoing a change. So maybe that is a coffee mug and looking at the temperature change of the coffee mug undergoes. Maybe that is a reaction and thinking about, let's study the reaction. Does the reaction give away energy? Does the reaction absorb energy, right? It doesn't necessarily have to be a physical thing. A reaction is a process or a change. The surroundings is everything outside of that. But typically we want to make it a little bit more narrow, and we just think about it what is just around the system. So for example, if we're thinking about the coffee mug, it could be something around it causing it to release or absorb energy. Or reaction, maybe I have a barbecue, and that barbecue, I turn on my propane, the propane reaction, the combustion releases heat, and that heat that's released goes into cooking whatever is around that, right? So that we're thinking about that as being the surroundings. Now, when we talk about systems and how they interact with the surroundings, we can broadly break these up into three categories. The first category or the ideas we want to think about is matter transfer or mass or energy transfer. Can they transfer energy? Can they transfer matter? And so if the system has the ability to transfer matter and energy between the system and surroundings, that would be what we call an open system. So an example of that is maybe just some open beaker where we have a reaction that's occurring. And this open beaker is going to be either releasing or absorbing energy as this reaction is occurring. Now, the way we can diagram that is we can think, well, I have this container where I have my system. And we notice that that system has an open lid. It's not sealed. And what that means is that I can have matter or mass coming inside and out of that. And we also have the ability for energy to go in and out. So we have the ability to transfer that. And a closed system is similar to that. It has the ability to transfer energy, but now what we've done is we've taken this flask or beaker, and what we've done is we go ahead and we seal it. So now anything that's given off is going to be stuck in there, whereas here we could have these gas particles leaving this container. But we do still have the ability for energy to go out. So now, as we're looking at this, we have matter does not have the ability to go in and out because now we have this sealed container. Whereas between our system and surroundings, we still have the ability for energy to go in and out. So we notice that we basically have sealed it. Then an isolated system means there is no transfer of energy and no transfer of matter. So this would be something perhaps where we have maybe like a hydro flask where now it's sealed and now we have our container in here. We don't have the ability for energy or matter to be separated. So now I have our system here, and now we look here, we do not have the ability for matter, nor do we have the ability for energy to go in and out. So there's a restriction where neither one of those can move. And so that would mean inside of maybe our system here, that's going to have a constant amount of energy. It doesn't have the ability to come out, and it's going to have a constant amount of matter. Well, in our closed system, we're going to have a constant amount of matter because we don't have particles going in, but our energy can change. So we see these different definitions of systems help us understand how energy possibly could or could not be transferred from the system and surroundings. Now, as we think of energy transfer, one of the important ideas that comes up is this idea of the first law of thermodynamics. This is the law that's describing the relationship between energy transfer between a system and surroundings. And it is the idea of law of conservation of energy. We can also consider it to be the same thing. Those are both the same. And this is where energy is not destroyed nor created, but only converted between different types of energy. And so if we're looking at this, we bring this back to our coffee mug example. So we have our coffee mug here, and into our coffee mug, we go ahead and we're going to add hot water. Let's go ahead and make this red to show that it's hot. So this water is hot, it's being put in this coffee mug, and what that means is that it's going to be given anything colder than it, it's going to transfer energy to it, specifically heat. Well, as it does that, that means that we're not destroying this energy. It's not just going away, and we're not producing energy that's causing our mug to get hotter. It's a transfer of that energy from the water to the cup. So what that means is that the heat lost by the water is equal and opposite to, and we're going to put a negative there to show that this opposite, the heat gained by our mug. And this is an illustration of this idea of law of conservation of energy. Or if we want to make it more broad, the heat gained by one thing is equal and opposite to the heat lost by another. And so what we're doing is we're mathematically expressing the relationship between heat transfer here between our water and, in this case, our coffee mug. So this is looking at heat transfer between objects and how this relates back to thermodynamics and this idea of, in this case, physical thermodynamics. Now that we have a kind of a broad description of energy, let's talk about how some of this energy gets manifested. And this relates to this idea of a state function and a non-state function. So a state function is a property of matter that can be fully defined simply by the current state the system is in. So that could be the temperature the system's at, the pressure the system's at, the mass the system has, the volume the system occupies. There's all these different things that can help us define a state function. So we notice here, there is no change needed for us to actually define this state function. It's just present. We have the ability to identify it. So an example of this is temperature. And the reason why we could say this is a state function, I could go ahead and take a thermometer and put it into any system and measure the temperature. So that means I'm going to measure the temperature of that system using a thermometer. Doesn't matter how it got there, just measure that its temperature. Well, let's go ahead and define temperature. Temperature is the measure of the average molecular kinetic energy of a system. And why are we going to talk about average? And what that means is not all of the molecules in that system have the same kinetic energy. What we'll notice is that we can think about this as being a kinetic energy distribution. So we have number of molecules or atoms or ions, however we think about it, particles if we want. And we're going to look at a kinetic energy distribution chart. This is just like a height distribution chart. Maybe if you go into a room and you measure all the heights of every person, you could draw out a diagram that shows the distribution of these. But this would be the kinetic energy of that molecule or atom. And if we're at a specific temperature, if we just go ahead and measure like a bunch of data points of the number of particles that we have at different kinetic energies, and we were to draw on a smooth line that fits this, what we'll notice is we get this smooth distribution. And what that tells us is that, I'm going to call this just T1. At this temperature, we have this distribution of kinetic energies. And if we were to add up all these kinetic energies, we would find that we'd have some average kinetic energy. Well, that average kinetic energy is what's proportional to our temperature. But we do notice that we have some low kinetic energy and we have some high kinetic energy molecules. Well, now let's say we go ahead and we warm up this system. And now we measure our distribution again. We measure this distribution again, and again we get some average kinetic energy, and we're going to call this T2. We'll notice here is that T2 is a higher temperature than T1, which would make sense because our kinetic energy, our average kinetic energy is higher. Now what we notice is that we have more high kinetic energy molecules, and we have fewer low kinetic energy molecules. And again, this is comparing the higher temperature to the lower temperature. But there still is this distribution where we have some very high kinetic energy and some very low kinetic energy. But what we do notice is that if I were to go in and measure the average kinetic energy of a system, aka the temperature, it doesn't matter how I got between these 2 points. It just matters that I'm at a specific temperature. And we'll see that this is important as we think about the connection to this of a non-state function. This is our state function of temperature. Now, a non-state function is a property that only has meaning based upon the path a system takes or the change that system undergoes. So for example, this has no meaning if there is no change. We cannot define something that is a non-state function unless a change occurs. So an example of this would be heat. Heat is a measure of the transfer of total kinetic energy between two objects. So in order for heat to be transferred, or in order for us to measure heat, by definition, we are measuring the kinetic energy transfer. We are measuring the change in kinetic energy when this process is occurring. And so when we look at our non-state function of heat, it has no meaning unless we transfer kinetic energy or unless a change is occurring. So again, maybe let's say we have are high kinetic energy, also are higher, let's just call these higher kinetic energy and higher temperature. And then we also have another object that is our lower average kinetic energy or lower temperature. So as soon as we allow these objects to come in contact with each other, what's going to happen is that we're going to have this movement of kinetic energy. So it's going to move from a higher to the lower. So in this case, we're going to have kinetic energy flow from the high kinetic energy to the low kinetic energy. That kinetic energy movement is what we call heat. It's a transfer of this molecular kinetic energy that's moving. And this will continue to transfer where we would have our heat transfer until the average kinetic energy of both objects are the same. So we're going to continue to transfer this kinetic energy until both the kinetic energies of them are the same. Or we could also say that the temperature of both are the same, because we know that our average kinetic energy is the same as temperature. So we see that now we've observed this idea of this non-state function of heat, or the transfer of kinetic energy, and how we can connect that back to our state function, which we can measure, which is temperature. And so in our next video, we're going to look at connecting this idea of heat transfer to measuring temperatures and how we can quantify that.